And, stay positive. I told you that you were going to fail more than you were going to succeed, right? I did say that. So stay positive, but you've got to put in the time, I know that this stuff is not simple, but I think today you're going to see it's going to get even worse. So, I don't know. I think a lot of it is psychological. You have to go into it with this mindset of, it's me against the problem, and, I'm going to beat it. I'm going to do it, Okay, how about the first one? Was the first one tough?
Yeah.
What's the substitution that we need to make on the first problem?
X squared minus 4x
Okay,
plus 5.
so we take x squared minus 4x plus 5 is our U substitution. And the reason we're doing that is because we're looking for something in its derivative, right? And I kind of have that, don't I? I kind of have it. Du is 2x minus 4 dx. I don't quite have a 2x minus 4, but I have 4x minus 8, which is this times 2, right? So you have two options at this point. You could factor 2 out and then pull that out of the integral, or you could take this equation right here and just multiply both sides by 2. Either way, right? I'm going to choose to multiply this by 2. So 2 du is going to give me 4x minus 8 dx, right? And now that I have that, I should be able to replace everything. I know I turned this on, but flip this over. Okay. So if I do this now, and I rewrite this integral, the 4x minus 8 dx, this whole thing all together, right, is 2 du for me, right? It's going to be 2 du. And then what's left is 1 over this, right? 1 over this. So that should be 1 over the cube root of u, right? Because u is x squared minus 4x plus 5. And then the rest of it was 2 du. And then I can pull the 2 out completely from the integral. And then I can rewrite 1 over the cube root of u as u to the negative 1/3 power, right? And now at this point I can use the power rule. So the power rule says that the antiderivative of this will be 2, which just comes along. Then I'm going to do 1 over this plus 1 and blah, blah, blah. So we should get 3/2 u to the 2/3. So adding 1 to that gives you 2/3. And in front it's always the reciprocal, so, and then plus c. And then these 2's cancel, and then you get 3. And then you can just replace u now. U is x squared minus 4x plus 5. And then to the 2/3 plus c. And if you wanted to, you could rewrite this as the cube root of this thing squared, but you could just leave it like that also. Okay? So I would say maybe the trickiest part of this problem is realizing that you actually do have this here. If you just have to scale it by 2, right? Okay. Now the next one, I only had 2 people in my other class get the next one. Did anyone get it? Feel like you got it? What's the U substitution on the second problem? Okay, let's try that. Let's see what happens if I do U is equal to 1 plus e to the 2x. What would the derivative of that be? E to the 2x times 2 dx. That's just a little chain rule in there, right? The problem is I don't see this anywhere. Like if this whole bottom is u, this is not du because it's e to the x, not e to the 2x. So how are you going to make this into that? Yeah, you can't quite do 1 plus e to the x, but you can do something close to that. Do you all see that this is not going to work? Did anyone try this and then do something right now that you want me to try? Like, does anyone want me to continue with this?
I split up the e to the 2x to 2,
To what?
like to e to the x plus e to the x. That's like
E to the x.
plus e to
Okay, that would be a problem. It would have to be e to the x times e to the
or
x.
e, yeah.
You, right? Because if you have the same base, e, and you multiply, you add the exponents, right? And x plus x is 2x.
I think it's
That still doesn't quite help. Should I keep going? I think that's going to be a problem.
You can't take the square root of it, can you?
Nope. Nope.
You can't pull out a e to the x
Where?
from there. Is it like e to the x du equals e to the x?
You could divide both sides by e to the x,
Oh,
right? Like, okay, so I think what you're saying is you have an e to the x dx, right?
yes, sir.
Okay, so why don't if I divide this side by e to the x, and why don't we divide by 2 also, that way it'll match up exactly. Then wouldn't this side be 1 over 2 e to the x like that, and these are gone? Now it matches, right? E to the x dx. Okay? We still have a problem because this has u's and x's in it, right? And we're trying to switch from x's over to u's. So this is still going to be an issue. But you might actually still be able to do this way. You could solve for e to the x where, though? You'd have to use this equation. So how do I solve for e to the x? Not e to the 2x, but e to the x here. I would have to move the 1 over, right? E to the 2x. And then what? Now we're trying to solve for e to the x. Divide by e to the x again, and then see you're going to have e to the x still. Well, if I change that, if I like take log on both sides, I'm going to get 2x over here, right? And then I'd have to plug that in here. So that e to whatever this side is, which would be like natural. I think that's going to get a lot uglier now, right? Because now you're going to have a new integral with natural log over u. It's going to be kind of messy. All right, there's a basic substitution that works here, and this is not the one. So there's something you have to realize, all right? And I believe this came up in the homework. I believe it did. I'll have to go back and look. If it didn't come in the homework, I'll consider giving both classes credit for this problem. But this right here really means what? E to the x times e to the x, right? Which is the same as e to the x squared. That's the same thing, right? Something to a power, you multiply the powers. 2 times x is 2x. Do you see this? Now, what if I make this e to the x my substitution? What's the derivative of that? E to the x dx, which I have right here, don't I? And so this integral, if I switch it over now, becomes, well, this is going to be what? This right here is going to be du. So I have 1 over what? 1 plus u squared du. And the do y'all see that? And the antiderivative of this is arctangent of u plus c. And then you just replace u with e to the x. So you have to first realize algebraically that e to the 2x is e to the x squared. And then it works. So what I would have anticipated you did is maybe try this whole thing as your U substitution, see that you're running into a problem, scrap it, and go to a different approach. Okay. It's just one quiz. I had a student tell me, that they were thinking of dropping because of this quiz from yesterday. I'm like, not yet. It's not time. All right, we started doing integration by parts, right, last time? Yes? And I put the formula on the board here for you, just to remind you of what it was. So before I get into these examples, I wanted us to look at something real quick that's going to come up a lot. So I want to try and see if we can't derive some sort of formula. Let's take a look at this integral. Let's say we have like integral of cosine of ax plus b dx, where this in here is linear. You'll know what I mean by linear? It's a linear expression, ax plus b. The highest power on x is 1, right? So that's a linear expression inside of a cosine function. If I try and find the antiderivative of this, I'm just going to take a guess right now as to what it is. I'm not going to do substitution or anything else. I'm just going to guess that it's probably going to be sine of ax plus b, right, plus a constant. Like, that's a pretty good guess. Would you agree? But the problem with this is that if I take the derivative of this, I will get cosine of ax plus b, right? But then chain rule would have me go in here and take the derivative of ax plus b. And what's the derivative of ax plus b? Just a, right? So we're assuming here a and b are constants. So derivative of ax would be a, derivative of b would be 0. So I would get an a that popped out, right? So what I would need to do out here is put a 1 over a out in front. And that way when I take the derivative of this, I ignore that. Derivative of this is cosine of ax plus b. Derivative of the inside is a, but then I kill off that a and I get this, right? Do y'all see how that works? You sure? Okay, so let's do a specific example. What would the antiderivative of that be? 1/4 sine 4x plus c, right? Because you identified that this was a linear expression. This only works for linear expressions, right? Because if this is something other than a linear expression, this chain rule causes other things to happen. That okay? How about this one? Cosine of pi x minus 1 dx. 1 over pi, because pi is a constant, right? 1 over pi sine pi x minus 1 plus c. All right? So this is kind of like a general formula now. Anytime we're trying to find the antiderivative of cosine of a linear expression, it's just going to be that 1 over a sine of the linear expression plus c. Now, how would this change if I try and do the same sort of thing for sine, if I'm trying to find the antiderivative of sine? A good guess would be what? Cosine, right? Of ax plus b plus some constant. But when we take the derivative of cosine, it's negative sign, isn't it? So I would actually need a negative out here. And I would still get the a to pop out, wouldn't I? So I need to kill the a off. So I need a negative 1 over a out front. That make sense? So let's take a look at a specific example of this. The antiderivative of sine of 4x dx should be what? Negative 1/4 cosine of 4x plus c. So this will save us a lot of time later, not having to actually go and do a substitution if we just remember what happens, all right? I'll give you one more. What is the antiderivative of sine of 5 minus x dx? Be careful here. Okay, so a in this problem was 4, right? So we put negative 1 over 4. A in this problem is what? Negative 1. So we're going to put negative 1 over negative 1, which is positive 1. Right, we're doing negative 1 over a, but a is negative 1, so then cosine of 5 minus x plus c. And that's just 1 out there. You okay with that? Yes?
You just write that as cosine.
Yes, that's what I would do. Yeah, I just wanted to illustrate that I'm using this formula. Negative 1 over a, this right here comes from that. Yeah, but at the end of the day, it's just cosine of 5 minus x. All right. So last class we were doing integration by parts, and I did that in-class quiz. And has the packet gone around? Has everyone had a chance to get their stuff?
Yeah.
Okay. So you all did pretty good on that. So you've seen how sometimes we can use integration by parts to repeatedly, right, to get an integral. So in these examples that I have in my notes, the first integration by parts is the first one there we are not going to do, okay, because that's something like we talked about last class. But I am going to do part B. I didn't do these, right? I just made some up. So I'm going to do part B. And this example, the statement here that I have to the side says that this is an integration by parts problem, but it's not so obvious that it is an integration by parts problem. So reminding you from last class, what we had with our integration by parts is we were looking for like two functions, and we knew that when we used integration by parts, the new integral was going to transfer the derivative, so you were going to take the derivative of one of the functions and integrate the other function, right? And that was very useful for a problem like this, right? Because I have x times sine of 10x. So if I do integration by parts on this one, and I choose that to be u, we know in the new integral it's gone, right? It's a 1. But in this problem here, what's kind of fundamentally different about this as opposed to the problems we did in class last time with integration by parts? What's that? Yeah, I mean, it's just one single function, right? Like, so how am I supposed to use integration by parts if I just have one function? Right? Does that seem a little strange? So this is why I call this a not so obvious integration by parts problem. Now, I have to choose, well, we could go through and think about all the things that we know and kind of get to the point where we have nothing but integration by parts, right? This is not a common formula. You know the derivative of this, right? But you don't know the antiderivative. It's not a power of x, a basic u sub. I don't see something in its derivative, right? So I don't think we have much hope. It would be nice if I took that little -1 away, because I just gave you a formula for that, right? But no. So that really means the only thing we have left on the table in terms of our techniques is integration by parts. And this is what I was trying to say in that email yesterday, is that we want to attack this problem with whatever we have, right? And what I have right now is integration by parts, right? That's probably the most powerful method I have up to this point. So with integration by parts, my choices are, I've got to make this table, I've got to choose a u and a dv, and those are always my choice, right? I need two things. I don't have two, well, I do have two things, right? That's multiplication, right? So one of them is sine x and the other one is dx. So why don't we choose u to be this? If I choose this to be u, I better know what the derivative of it is, right? Go back to the formula. If I'm going to choose something to be u, then in the new integral, I'm going to need its derivative. So you better be able to take the derivative of whatever you have, right? And then the other part that I'm going to choose, dx, that's going to be my dv, right? And that means in the new integral, it's going to get integrated. And what's the antiderivative of 1 dx? X. So arcsine of pi x goes here, and dx goes there. Now let me show you something before we continue with this. What if you came in here and you were like, all right, I'm going to do my u and my dv. Your only other option would have been to do this here and that there, right? That would have been really your only other option. And do you see why this is just bad? Because in the table, don't you have to go up from here? And you don't know the antiderivative of that. That's the original problem, right? I mean, you're never going to be able to go like this. And here, you're taking the derivative of the derivative. So you'll be like second derivatives. It's going to be, it just, do you see it just doesn't naturally fit this way? But here it does. Okay, so let's do this. I'll go up here first. V is going to be 1, right? Not 1, x. And du, well, we learned what the derivative of arcsine of something is. It's 1 over the square root of 1 minus whatever was in there squared, right? Where am I getting that from? Like first day of class, right? So that's the derivative. I'm just going to take the pi x and square both the pi and the x. So I get pi squared x squared. That okay? And then, am I done? No, times what? Derivative of what's in here? Pi. And then dx. Do not forget the dx there. Now, do you feel like I stressed this enough to you last class that in the new integral, you're going to multiply across, like these two are going to be multiplied, that's u times v, and that your new integral is going to be the diagonal? If I didn't stress that enough, I want you to start to kind of burn that in. In our new integral, it's going to be this times this, minus the integral created from this diagonal, this times this. And I think if you look at this times this, right, you're probably going to throw up a little bit because you're like, wow, that looks really bad, right? With all that square roots and pi's everywhere. But let's just take it through, okay? Like I said, we're attacking this. This is the only thing we have. So let's not give up yet. This will become, according to integration by parts, u times v, right? So this times this. So I'll just write it like this. X arcsine pi x. See, and I don't have to do any integration there. It's just multiply them. Great, beautiful. And then minus, now here's where the integral is going to come in. And I like to always leave a little bit of space out in front of my integral to pull any constants out if I have them. So when I do this times this, do I have any constants that I can pull out? Just that pi, right? That's the only thing that can come out? So let's go ahead and pull the pi out. And then let's do it. It's going to be x times 1 over root 1 minus pi squared x squared dx. I said something earlier. It may have come out wrong. I said, you know, don't go drop the class yet. I didn't mean that. I meant that like one quiz is not like a deal breaker, all right? Now, first exam is a 20, then we need to think about things. But I'll give you this advice. No matter what happens here, I think you need to see this course all the way through. Even if you drop it, see it all the way through. Come to class, because sometimes you have to see this class twice or 3 times to actually get through it. I'm being real. I have really good students that have gone on and done engineering programs that had to take Cal 2 a couple of times. All right? But it's just very difficult to proceed from here if you just barely get by. It's just, you know what I'm saying? Okay. Crap, look at that thing. It just looks intimidating, doesn't it? Did we even make any progress with this? What can you do? We could do integration by parts again. Let's think about what that would entail. Let's just real quickly think about it. If I did that, what would you choose for your u? Well, okay, what's inside here? You mean for integration by parts? Or u sub? U sub. That's what we want here. Okay? Integration by parts actually, again, is just going to make things more complicated. All right? So what we need to see here is, like, once we get to this point, we reset everything, right? We go back to our techniques. What do we know? Can we attack this integral? And u sub is one of our techniques, right? So do we see something in its derivative? Yeah. So you said let u be equal to what's under the root. 1 minus pi squared x squared, right? The derivative of this is, well, derivative 1, 0. Negative pi squared is a constant, right? So derivative of x squared is 2x. So this is going to become negative 2 pi squared x dx. Right? So I'm using U sub here. I'm not using integration by parts. And are we okay with this? Like, are we happy to see this or what? What does our original integral have? Original integral has x dx, right? But here's x dx. And I can just get that to the other side and I'm there, right? So just divide both sides by negative 2 pi squared. This is a constant. We're off by a constant. That's okay. So 1 over negative 2 pi squared du equals x dx. And that's it. So we can keep going here. So let me do this. Let me just kind of recap where we are. What we're doing over here is we were trying to address the integral x times 1 over root 1 minus pi squared x squared dx. We were trying to do this integral, right? Which is this right here. Okay, that's what we're trying to do right there. When we did that, we did a basic U substitution, blah, 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 blah. And what does this new integral become? So we know that this is this thing, right? So it's all that. And then whatever's left was 1 over what? 1 over root u. Right? 1 over the square root of u. That was our U substitution. And then the rest of it is just 1 over negative 2 pi squared du. I can pull this whole constant out. So negative 1 over, you know what, I think I'm going to do this up here. So y'all can see it. So now I'm at negative 1 over 2 pi squared. Integral of 1 over root u is the same as u to the negative 1/2 du.
Could you go ahead and include pi in the numerator?
Could I include the pi in the where?
Numerator of the constant?
How?
Or isn't that pi getting multiplied by
Oh,
the...
it means the one down there.
Yeah.
Oh, no, I'm not going to do this yet, okay? Everything in this orange box is all of what I'm doing here. And when I'm done, I'm going to take that answer, I'm going to stick it right here.
Okay.
And then I will bring the pi in.
Okay.
Okay. So look at this as like scratch work, right? I'm doing this on the side, trying to figure out what this integral is. All right, this becomes negative 1 over 2 pi squared times, now just use your power rule on that. And when you do your power rule on that, I believe you get 2 u to the half. Okay, 2 times u to the half. Plus c. And these twos cancel. So at the end of the day, I've got negative 1 over pi squared square root of u, right? Now I don't need the plus c, okay? I put the plus c because I'm just so used to doing plus c, but this is all part of a bigger problem. So what I'm going to do is at the very end, I'm just going to do plus c, all right? Now what was u? This right here, yeah, 1 minus pi squared x squared. All right. That right here is this right here, right? So now we're ready to put it all together into a final answer. The antiderivative of arcsine of pi x is x arcsine of pi x minus pi, and then times negative 1 over pi squared square root of 1 minus pi squared x squared, right? That's this thing getting plugged in right there. And then plus c at the end, all right? I forgot to put my parenthesis around here. There we go. Now let's distribute that pi through, okay? It's not actually not distribution because there's only one term here. So that pi is going to come in here. The negative and negative is going to become positive. So this will be our final answer. Equals x arcsine of pi x plus what? 1 over pi root 1 minus x, pi squared x squared plus c. Wow, okay, there it is.
Would we have made any progress if we had put like dv is pi x?
Pi x where? Oh, in the original problem?
Yeah.
Okay, so this is arcsine. This is the original problem. You cannot use pi x as dv because pi x is inside of a function, so it's not being multiplied. In the formula, your dv has to be multiplied times something. And pi x is its composition, it's inside. It's the argument of arcsine. So no, this is not like a multiplication right there. I don't know if that's what you mean, but yeah.
Well, yeah, I was thinking.
Yeah.
It's like
Yeah.
saying sine -1 of pi x, not sine -1 times.
That's right.
Yeah.
But I think what you're saying is, could we have done a basic U substitution of pi x to start?
Well, no, I didn't think about what we were doing there.
We could have. You could have done a basic substitution of u is equal to pi x, and you would have transformed the problem a little bit, but
And you don't know that.
then you still have to do integration by parts. You still can't get around it. It just saves us the pi's kind of, don't have to deal with them as much. Okay, so this is it, right? We're done? So this was a not so obvious integration by parts because we only had one expression there, but we were still able to do it. But in doing it, we actually had to do a basic U substitution after we did the integration by parts, right? So we've seen the quiz last time, you can do integration by parts multiple times. Here, you can do integration by parts and then have a substitution afterward. I don't believe that that's the antiderivative. Do you believe that that's the antiderivative?
Prove it.
I could check it, couldn't I? I could, right? How long would it take us to check that? Not long at all. Okay, check it out. I'm just going to show you that this is right. This is a product, right? Okay, that's a product, so I can use product rule. Let me see if any of these red ones work. That's decent. Terrible. All right, so let's try this. When we do product rule, derivative of this, 1 times this. So we have arcsine of pi x plus the derivative of arcsine of pi x, 1 over square root of 1 minus pi squared x squared times the derivative of what's inside, pi, times the first function, x. Right? That's your product rule? Okay, plus now the derivative of this. Now 1 over pi is a constant, so it's just coming for the ride. Now what's the derivative of the square root of something? 1 over 2 roots of that something times the derivative of what's inside of it, which is negative 2 pi squared x, right? And I'm done. 2's cancel. One of the pi's cancels. And this right here is pi x sitting on top, right? And this right here is pi x negative sitting on top. So they're the same exact things, but opposite of one another. So this whole thing cancels with this whole thing, and all you're left with is this. Right? Yes? Yeah, you'll see it? It works. How? Like, nobody is going to just sit here and look at arcsine of pi x and tell me the antiderivative. If you can, then you don't belong in this class, all right? Because that is a very complicated antiderivative, isn't it? To see all of this happening is impossible. That's why we have to have a method, an approach to systematically get us to where we need to go. How do y'all feel? Are y'all up for this challenge? Okay, let's look at the next one. So part A I said I'm not doing because I did one like that in class last time. Part B I just did, that's not so obvious. Part C is a repeated integration by parts. I gave you a quiz on that last time, right? But I'm still going to do this one because I want you to appreciate how putting that beta t, beta is a constant, like alpha, beta, gamma, that's just a constant. I want you to see how having that beta in there really throws it just complicates everything, all right? But we have to be careful and persistent. All right, there we go. So I hope you look at that and you realize, look, I'm just going to have to do integration by parts twice. And I have everything with t's instead of x's, is that all right? So I'm going to have to do integration by parts twice because the first time I do it, I'm going to use that for u. It goes over into the new integral, becomes t, right? 2t, but who cares about the 2, right? And then when I do integration by parts again, that t is going to become a 1, and then I'll be good, right? Okay, so let's do it. Let's set up the table. So the table becomes u and dv. And u here for us, we said was t squared. And cosine beta t dt is dv. We have no other choice. And isn't beta t linear? So when I go up to v, what do I get? 1 over beta sine beta t. When did I show you that? About 20 minutes ago, right? I showed you how this goes to this, okay? And then coming down on this side, this one's just 2t dt.
Yeah, we're doing the homework and I thought we were just, like.
What, this? Yeah. Okay, ready? The new integral becomes across here, right? This times this, which I'm going to put 1 over beta out front. Then I'm going to put t squared, and then I'm going to put the sine beta t. Yes? Minus, I'm going to leave a space, integral. I'm going to pull any constants out of the diagonal, this diagonal right here. So what are my constants? A 2 and a 1 over beta. So 2 over beta. And then everything else that was there. So I had a t, I had a sine beta t, and don't forget the dt also needs to be there. Okay? Now, this one right here is a separate problem. Trying to do integral t sine beta t dt. So I set up a new integration by parts and let u be t, right? And dv be sine beta t dt. du is dt. I'm happy to see that. It's basically we've killed off that power of t. And then I integrate this side, and we just talked about this. This will be negative 1 over beta cosine of beta t. That's it. So now, using the integration by parts formula on this integral, I get this times this. So I'm going across here. How about I do it this way? Negative 1 over beta t cosine beta t. That's u, that's ultraviolet. And then minus space integral. And what constant can I come out with here on the diagonal? Negative 1 over beta, right? Can come out. So why don't I change this to a positive, because I'm going to have a double negative there. 1 over beta. And then all that's in there is cosine beta t dt. Any questions? Yes?
Well, you have negative 1 over beta t. Could it be negative t over beta?
Yes, you could do negative t over beta. That's fine. All right, we need one more antiderivative, this one right here. And see, no more t in front, so we just go straight to the formula. This will be, what's the antiderivative cosine beta t? 1 over beta sine beta t. But I already have a 1 over beta. out there, don't I? So 1 over beta t cosine beta t plus, I have this 1 over beta, and then this one gives me another 1 over beta, right? So 1 over beta squared sine of beta t, right? And then plus c, but I'll throw my plus c in later. So this right here is it. This is the part in orange that needs to get pushed back in there. So we've got 1 over beta coming back here. T squared sine beta t minus 2 over beta, big old parentheses, you could use a bracket if you want, minus 1 over beta t cosine beta t plus 1 over b squared sine beta t, close my parentheses, plus c. I think I got it all in there, yeah? And what would be kind of the last step here? Distribute. This is going to go here, and then this is going to go here. And when I do that, I'll go ahead and write it out. I get, well, let's put it up top. We get 1 over beta t squared sine beta t. And then here to here, the negative and negative is positive, so I get plus 2 over what? Beta squared t cosine beta t. All right, and then when I go from here to here, still have a negative. Negative 2 over beta cubed sine beta t plus c. That is the antiderivative of t squared cosine beta t? Is that what it was? Yeah. If we took the derivative of that, we should get t squared cosine beta t. No thanks, I'm not going to do that. But we could, right? Like this is a product rule right here. Then this is another product rule. And then this one is not a product rule. Questions?
At the beginning,
We're
how did
okay?
you go from outside the orange brackets? Where did you? It was like 1 over beta at first, and then you made it 2 over beta.
Because you're
Here?
distributing.
Up one, right there. Yeah. How'd you get that 2?
In my first integration by parts table, which is no longer on the board,
Yeah, I have it here.
the
it
derivative
was,
of t squared was 2t, and that 2 it came out with that 1 over beta.
Wouldn't that have been 1/2?
No, it's 2. The 2 comes out as a 2 on top. Like it's a 2 on top, and then
Like right here is what you're saying? 2t dt? So,
no, you're not solving for dt. You're taking this and multiplying it times that.
oh, okay.
Yeah.
Yeah, so it's not like U substitution where you're trying to get something to match.
Okay.
You're just going to make your table and then just go across and then the diagonal. Okay. All right, well, I mean, so far. Oh, by the way, there are people who teach some shortcuts for this, like when you have repeated integration by parts like this. And I've seen it, and I know of it, and I could teach it to you all, but I'm just not a big fan of shortcuts that only work for one type of thing. So I'm not going to show it to you. All right? All right, next one. Rabbit out of a hat. Okay, so up to this point, everything's been pretty, well, I'm not going to say straightforward, but this next one, rabbit out of hat, implies in some way it's kind of magical in a way, right? E to the 2x cosine x dx. So again, last class I was really trying to stress to you that the integration by parts formula is a transferring of the derivative, right? You start with an integral, you've got two things. In the new integral, you have the derivative of one of them and the integral of the other one, right? They kind of switch places. Do you see something problematic with this if we use that idea? If I choose this to be u, what's it going to be in the new integral?
More than that.
Still e to the 2x, right? I mean, yeah, we'll have a 2 pop out, but I mean, it doesn't get any better. Like t squared became 2t, right? And then I did it again, the t went away. But if I use e to the 2x as u, it doesn't matter how many times I do it, right? E to the 2x is always going to be there, right? So, okay, maybe I use the cosine x, right? Well, if I use cosine x, what's it going to be in the new one? Negative sine. And then we'll still have the e to the 2x there because I'll have to integrate this, right? And the antiderivative of e to the 2x is still itself. So it keeps on, like, it looks like no matter what I do, I'm going to get an e to the 2x in sine or an e to the 2x in cosine, right? So it doesn't seem like this integration by parts would work. But it does. Okay, so let's see. So I'm going to choose u to be e to the 2x. And then this, I'll let be cosine x dx. Now let's just see what happens. All right? So the derivative of e to the 2x is 2e to the 2x dx. That 2 comes out from chain rule, right? And then the antiderivative of cosine x dx is just sine x. So according to integration by parts formula, this will be ultraviolet, these two, right? So e to the 2x, sorry, sine x minus a little bit of a space there, integral. Can I pull a constant? 2? Let's pull a 2 out. The 2 comes from here. And then I still have e to the 2x dx and sine x. So e to the 2x sine x dx. Any questions on that part? That okay? So this new integral did not get any better than that one, right? All you did was basically replace the cosine with sine, but we're still kind of stuck, right? All right, let's do it again. Let's just do integration by parts again on this one. Okay, so I'm going to step away from this. I'm going to do that over here on the side. Trying to do integral e to the 2x sine x dx. I do a little integration by parts table. U is e to the 2x, dv is sine x dx. Du is 2e to the 2x again dx. And what's v? Negative cosine x. All right. According to the integration by parts formula, this will become these two multiplied and then minus the integral across this way. So these two multiplied are going to be, what's negative e to the 2x cosine x. And then minus space integral, any constants I can pull out of this diagonal. I can pull the 2 and the negative, right? So when I pull that negative out, it's going to turn this into a positive, and we'll have a 2 here. And what's inside that integral? E to the 2x cosine x dx. And I should look at that and probably start getting upset, because now I'm back to the original integral, right? I mean, that's the original integral. And it appears at this point that this is not doing anything, right? Don't worry, we're not going to do it again. We're not going to go again. What we're going to do is we're going to take what's in orange and we're going to plug it in over here, all right? And then distribute the negative 2 through, all right? So let's just see what happens.
Would that kind of help a little bit?
It's going to help tremendously, but let's do it first. Okay, so I'm plugging into this. Here's my negative 2. I've got minus e to the 2x cosine x plus 2 integral e to the 2x cosine x dx. Do y'all agree that that's just me taking this and plugging it in over there? Right? Okay. The next line I want you to do something special that we really haven't done up to this point. On the next line, I'd like for you to write this. I'd like for you to write the original problem, right? Just write that down. And then I want you to say equals, and then I want you to write this down. But I want to distribute this through, okay, the -2 through. So we're saying that this integral is equal to e to the 2x sine x, what? Plus 2 e to the 2x cosine x minus 4 integrals of e to the 2x cosine x dx, right? Who sees it? What now? I think you. Yeah, so look, we're saying, hey, look, this integral that we're trying to figure out is this plus this minus 4 of these, right? So algebraically, can't I just move this to the other side of the equation by adding it on both sides? I can add 4 integrals. I don't think you've ever done this before, all right? Sure, you've added 3 to both sides. Sure, you've subtracted 5 on both sides. But you've never added 4 integrals on both sides, right? That's what we're doing. We're algebraically just adding something to both sides of an equation. It's just that something that you're adding is this big old integral. Do y'all see that? And so what happens is on the right-hand side, it's gone, right? And on the left-hand side, what do you have? 5 of them now, right? 5 of them. 5 of these integrals that we're trying to find is equal to e to the 2x sine x plus 2e to the 2x cosine x. And notice there are no more integrals over here, right? So all we have to do to get the integral is divide by 5. Right? Divide both sides by 5 and we have it. I know, right? Isn't that kind of cool? Now, there is one slight little issue. You have to remember the plus c here. Okay? Because this is the antiderivative, it's got to be plus a constant. So let me divide everything by 5. Go ahead, man, crank it. Get it done. Doesn't bother me. All right, so we have this integral e to the 2x cosine x dx equals, I divided that by 5, it's gone. Here I divide each one by 5, right? So what if I do 1/5 e to the 2x sine x plus 2/5 e to the 2x cosine x, and then I just remember it's the antiderivative, so I have to do plus c.
So the c doesn't get divided by 5?
It doesn't matter because c divided by 5 is still a constant. So I could call it c divided by 5, but it doesn't have to be. See, that constant you never have control over. So if you want to multiply by 2, go ahead, it's still a constant,
Can't really
right?
anticipate what it would
That's right. It can be anything, right? It can be any constant.
Any number.
Any number, right. Okay, there it is. There it is. That's a very interesting type of problem. These come up, you know, the thing that kind of tips you off that the problem's going to do this is when you have 2 functions in here that neither one of them seem to get better, right? Like as you use the integration by parts, neither one of them goes away. Does that make sense? Okay. Just tell me if you believe this. Is that the same thing? So I just pulled out a 1/5 e to the 2x. Now, the reason I did that is because I want to prove that this is the antiderivative. So I'm going to take the derivative, and there's a product right there. Okay, so real quick, I'm just checking my work. The derivative of this is 1/5 e to the 2x times 2. Then times the second function. And then plus the derivative of this, which is times the first function. Right, there it is. Okay, now let's start distributing. Let's see, this right here, let's just make that 2/5. So if I go here to here, I get 2/5 e to the 2x, right? Sine x? Yes? Do y'all see that when I do this to this, I get the same thing but negative? So those are going to cancel out, right? When I do, so I'm just going to put that in orange. Gone, that one's going to be gone. When I do this times this, what do I get? 2 times 2, so 4/5 e to the 2x cosine x, right? And when I do here to here, what do I get? 1/5, so I'm adding 1/5 e to the 2x cosine x. And 4/5 plus 1/5 is 1, so I get one of those e to the 2x cosine x's. All right, it works. I realize that some of you have seen Cal 2 before, all right? And many of you haven't. And this is really like, this to me is like where the journey begins. Like this is it. The journey is now officially begun for Cal 2. I'm excited for you, okay? This is really a chance for you to raise your expectations of yourself and start to feel like like you're engineering, computer science, like now you're starting to get into like mathy stuff. Does it kind of feel that way a little bit to you? Okay. So I'm excited for you. I'm here to support you best I can, but at the end of the day, you got to do the work. All right, let's look at the next type. So we pulled the rabbit out of the hat. It was pretty awesome. The integral wound up appearing on the other side, and then we just brought it over. Look at this one. This one says we have to make a U substitution first. We've done a problem already, haven't we? Where we did integration by parts. We did integration by parts, and after we did the integration by parts, that new integral, we had to do a basic U substitution, right? This one, I'm telling you, this is a huge hint, that you have to do a basic U substitution first before you can do anything. Root x? Root x? Yeah. So that would be a good guess. I mean, with substitution, I'm supposed to be looking for something in its derivative, right? There's nothing in its derivative here. Not that I can see. But we also learned that with substitution, sometimes if you just make the substitution, it works, right? Now, can we rule out some other things? I mean, like our other basic stuff, like the antiderivative of this is not just e to the root x, right? Okay, because chain rule would cause problems with that root. So let's try that substitution first. Let's go with u is equal to root x, okay? Let's just try it. The derivative of that, I'm using basic substitution, is 1 over 2 root x dx. Root x right here is my u. That's my root x, right? So that new integral would become e to the u. But that dx, I have not figured out what to do with yet. Because here, I have dx, but that means I would have to get rid of this, right? And we've seen problems with that before when you have x's there, because you wind up with x's and u's together, right? You know what I'm saying? But let's just try it. If I were to try and get this out of here, I'd have to multiply both sides by 2 root x, wouldn't I? Yeah. And that would be what dx is. And normally, this would be a problem, because I've got x mixed in here with u. However, what is root x? It's u, right? So this is actually 2u du.